solid, liquid, gas, and what comes next? Plasma, the fourth known state of matter. Not everyone is familiar with plasmas and what they're made of, but did you know that plasmas could be the key we are all waiting for towards a green technology of airlines? Having thousands of conventional air jets flying around the sky emitting vast amounts of carbon dioxide has been a major environmental issue worldwide. But recently, the discovery of the electric plasma jet engine shed light on how we can overcome this problem. So stay tuned as we discuss in today's video what are electric plasma jet engines and how can it help save our lungs from polluted air. But before we get into it, please do me a favor by clicking the like and the subscribe button and turn on the notification bell so that you'll always be notified anytime we release a new video. Close your eyes and now imagine what could be our situation if all the air in our atmosphere became dominated by dirt and carbon dioxide. Oh no, that's terrifying, right? It would be so hard to breathe by then. And guess what? The aviation industry could be accounted for this potential worst scenario, mainly because 2.4% of total carbon dioxide emissions globally is from this industry. According to the United States Environmental Protection Agency, planes account for 12% of all transportation emissions and 3% of total greenhouse gas output in America. If air travel continues its increasing trend, it's estimated that gas emission could triple its rate by 2050. This could worsen the condition of our atmosphere, leading to terribly polluted air everywhere in the world. But thanks to plasma, conventional air jets could be replaced by more ecological ones called electric plasma jet engines. Let's now examine these engines, how it differs with our conventional planes, and how it's made. Jet fuel versus plasma. First, you must take note that conventional jet engines work using jet fuel. Jet fuels are usually kerosene-based petroleum mixtures that are mixed with compressed air. The resulting gas heats rapidly and expands with explosive force through a nozzle at the back of the engine. Let's now compare jet fuels from plasma. Plasma is made up of charged ions and is comparable to a gas in that it has indefinite volume and shape and is less dense than liquid and solid phases. Plasma is made up of positively charged ions and negatively charged electrons that form naturally when molecules are ionized at high temperatures or high electric fields, like, for example, in thunderbolts and the burning of a star. Plasmas can be chemically superheated. An engine fueled by its expansion might provide enough thrust to propel an airplane. This concept is what scientists and physicists in the United States and Berlin are trying to break through a concrete project. But unexpectedly, the prototype of this concept was created by a scientist in Wuhan, China. Tang's discovered plasma propulsion using microwave. Joel Tang, a polymath in Wuhan, China, who worked at Caltech and Bell Labs, studied the use of microwaves in synthetic diamond manufacturing when he became curious if the same process could be used to create jet thrust. By then, he and his colleagues at Wuhan University's Institute of Technological Sciences devised a gadget that ionizes compressed air by passing it over an electrode and driving it down a precisely planned path. The primary idea is that by using microwaves to create energy from compressed air, electricity will be converted directly into thrust, resulting in plasma propulsion. According to the American Institute of Physics Advances, the team's prototype comprises a microwave power supply, a compressed microwave waveguide, and an air compressor and a flame igniter. The microwave air plasma jet engine thruster generates plasma using a high-powered 2.45 GHz microwave ionization chamber. The air is ionized, resulting in low-temperature plasma through a tube compressed by an air compressor. Temperatures in the plasma might reach 1000 degrees Celsius. According to a physicist on Tang's team, a steel ball weighing roughly 1 kilogram could be lifted using 400 watts of microwave power. In addition, the scientists determined that the device's jet pressure was 2400 newtons per square meter, which is equivalent to the pressure produced by a commercial airliner jet engine. Tang says what they have to do next is just to scale up the power of the microwave and compressed air to the standard of an actual jet engine. This will assure the production of the same strength of jet propulsion with traditional aircraft but without fossil fuels. Overall, Tang's team believes that a scaled-up plasma engine might be used to power tiny pilotless planes or heavy-duty drones to transport cargo for shipping within 5 years. But to be able to produce an air plasma engine for a large jumbo jet, he says it would require them another decade to create a massive number of megawatt microwave sources, high-powered turbine compressors, and a substantial amount of electric energy storage. Plasma used in space. The artificially produced plasmas are not a new concept. NASA employed this technique as part of the NSTAR NASA Solar Technology Application Readiness Ion Propulsion System. Ion propulsion is a relatively new technique that uses xenon, a naturally occurring gas, and electrical power. The fundamental procedure is splitting the electrons in xenon atoms to produce positively charged ions released at a high speed of 40 kilometers per second. This outlet speed is more than 10 times that of chemical thrusters, resulting in a propellant use that is 10 times more cost-effective than the power achieved. Artemis is the first European satellite to use electric propulsion technology in a mission, and if it succeeds, it will be the longest mission ever to run on ion propulsion. Going back, NASA has been utilizing electric plasma engines to energize xenon plasma in space for several years. It aids in the positioning of satellites and the propulsion of spacecraft across the solar system. In addition, less pushing is required with this method than chemical propulsion because of the thrust-to-propellant ratio. This technique aids in the reduction of expenses and the extension of satellite operating life. In previous expeditions, NASA utilized ion propulsion systems on a deep space mission from 1998 to 2001. This expedition, which was powered mainly by ions, went 163 million miles. Moreover, one of NSTAR's technologies, named Barley, is now in use on the Dawn space mission, launched in 2007, located in the asteroid belt between Mars and Jupiter. It's presently moving around the solar system orbiting planets Vesta and Sierras. Its updated ion thrust technology continues to be developed and improved. The NASA Evolutionary Xenon Thruster, which is expected to have 3 times the power of NSTAR for cost-reducing and lesser mission time. The barriers. But behind these amazing ideas about electric plasma jet engine, there are still holes that experts need to address to make the concept feasible. Simply put, we are not there yet because of the barriers. Plasma erosion is one of the significant drawbacks of Tang's prototype. The electric plasma engine may reach temperatures of over Haitian 1000-degree burns, which is simply too high for any aviation-grade machine to avoid plasma erosion. Plasma erosion is the deterioration of materials that come in touch with plasmas for a sustained time. With too much temperature, chemical corrosion, surface cracking, blistering, and embrittlement can all occur in light alloys and other materials, reducing components' service life dramatically. Moreover, there are also power difficulties in the team's prototype. Tang's microwave-powered Forester was capable of lifting a 1-kilogram steel ball through a tube with a diameter of 24 millimeters. Tang's experiment produced around 28 newtons of push per kilowatt. The Airbus's engines, a trio of 20s, create about 220,000 newtons of thrust. That means any plasma-powered aircraft would consume more energy than 7,800 kilowatts of electricity. And even if there is enough electricity that could be harnessed on an aircraft, the cabling necessary to get all of that to the plasma engines would be prohibitively heavy. For a 1-hour trip, you would need 2 570 Tesla Powerwall units, which is not ideal. In any case, a 320 can only carry roughly a third of that many Powerwalls, meaning there is no existing battery technology that could support getting this idea into a concrete project. People are now waiting for advancements in batteries or tiny fusion nuclear reactors to get over this barrier. Despite all the power difficulties, many experts think that the team's invention has tremendous promise. Although this amazing technology is still years away from being implemented as an electric plasma jet engine, it still promises a greener future for the aviation industry. What is more, it could be the key solution to help reduce humans' use of fossil fuels. What a great step to eliminating global warming problems, giving us the greatest privilege to breathe cleaner air. And that's it for today's video of electric plasma jet engines. Do you also think that Tang's prototype can replace conventional air jets? Do you believe that Tang's team will pull off this grand project despite the power issues? Can Tang's team think of a better prototype? Let me know your ideas by commenting down below. Also, don't forget to click the like and the subscribe button and turn on the notification bell so that you will be notified anytime we release a new video. Thanks for watching and see you in the next video.